We'll start off this next lecture looking at some practice problems. So we'll take a look at number 26 to begin, which kind of follows up what we were just talking about in the previous example we did in the notes. Explain the following trends in lattice energy. So we have the answer in front of us that this is the largest lattice energy, and followed by this one, followed by this one. Now, if we look at the charges, we probably, hopefully, should know that this is plus 1, minus 1, plus 1, minus 1, and plus 1, minus 1. So the charge thing we can forget about. So the only thing that really matters is the radius. These guys here are going to be the smallest atoms as far as the radius. So again, sodium, rubidium, cesium. So if we take a look at our periodic table, just for comparison, sodium, rubidium, cesium. And then looking at bromine and bromine, that's the same. And then chlorine, bromine is going to be lower than chlorine. So, yep, this one is going to be the smallest, and these guys will be bigger. So we'll just kind of say it this way. Larger radius provides smaller lattice energy. Or you can say it the other way around if you like. For part B, barium oxide and potassium fluoride, plus 2, minus 2, plus 1, minus 1. So the boron is larger because of the charges. Boron and oxygen. I said boron, I'm sorry, barium. Barium oxide has 2 plus or plus 2 and 2 minus or minus 2 charges. Providing for larger, let's say, lattice energy. For C, strontium oxide and strontium chloride. So strontium is the same, doesn't matter. Oxygen is 2 minus, chlorine is 1 minus. So again, the charge. So charge influences and just so I didn't mention it a second ago, but this is charge is going to be the larger factor. So chlorine, if we take a look at that, going back over, oxygen and chlorine, chlorine is smaller, I'm sorry, oxygen is smaller based on the fact that it is an energy level higher. So the size would also indicate that it's, the smaller is going to be a larger lattice energy as well. So charge influences lattice energy. And I would say more than size. But in this case, this is smaller and is a minus 2 in comparison to chlorine. So they both work in the same direction for this one. Okay, 41, I think I'll hold off on 41 for now. Let's go back to some notes. So before we jump into that problem, let's talk a little bit about polarity and something we didn't mention in the previous chapter, even though you might have thought it belonged there. Electronegativity. So electronegativity is kind of a combination of a few different factors, electron affinity and ionization energy, and how atoms are attracted to each other, specifically ions. So let's define a couple particles and how they would be attracted to each other. So we'll talk about nonpolar covalent. So again, these are like molecular, nonpolar covalent. And the ones that do this are diatomic molecules. So just to kind of expand on that, that means electrons are shared equally. So if you think about that, we have a couple examples. Chlorine, all the Hoff wrinkles, so we'll just write those guys down. Hoff wrinkles. These are all those diatomic atoms. So there's no pulling electrons more so one way or the other. Another example would be polar covalent. And for that, we'll say one element is more electronegative. And just so we are clear on this, if we're doing sort of a periodic table-y looking thing, electronegativity increases going in this direction because of Zeph, and it increases this direction because of size, less shielding. So again, it's the ability of an atom to attract electrons to it. Ability of an atom to attract electrons to it. They all have these arbitrary values, and fluorine has a value set up of 4. It's just completely made up. And every other atom has a relative value in comparison to fluorine. And that's it. So some decimal form, 3.7, 3.5, 2.1, something along those lines. Now for atoms that have nonpolar covalent bonding, that difference in their electronegativities. So we can consider a bond polar covalent if the differences in their electronegativities is something in the ballpark, and these are all just kind of a line that's been drawn, 0 to 0.4. And again, that's just made up, 0 to 0.4. And no, I said that incorrectly. Let me go back and fix that. It's like, that doesn't make sense. Nonpolar covalent, this is 0.0 to 0.4. These guys are 0.4 all the way up to 1.7. So polar covalent is somewhere in this range. Now, if you go above that, then it is considered ionic. So again, the ability to have a number within this range is going to be considered polar covalent, but if you get above this, so greater than 1.7, we consider that ionic. So again, it's just everything has an attraction. So sometimes we like to classify something as being a covalent bond or being an ionic bond, but it really is kind of a gray area in between. So it's how ionic or how covalent is it? And it's based on the differences in these electronegativity values. Let me again write something about that. That's this electronegativity. So again, that is the ability of an atom in a molecule. Just a letter in there. To attract electrons. So that's how we kind of define it. All right, let's do a problem back in our homework. So which of the following bonds are considered polar? And you don't have the data in front of you, and matter of fact, I don't have it in front of me either. But we'll get kind of a ballpark idea of how this would go. So boron and fluorine, looking at the differences, if I were to pull this up, and you have it in your book, actually, I'm not going to spend time to pull that out. 4 is fluorine by definition. Boron happens to have a value of 2. So based on the fact that that is a difference of 2, that would be the difference. As far as, well, which one is it? Is it polar covalent, ionic? I guess we call it ionic, but I'm not too concerned about that. These guys are the same, so there's 0. Selenium and oxygen. Oxygen is 3.5. It's pretty electronegative. Selenium is 2.4. And the difference is 1.1. So again, that would be nonpolar covalent. I'm not too worried about that. It just is. This one is 2.5 minus 2.1, giving us 0.4 right on that edge. It's not very polar. It's not a very polar bond, so it's shared fairly equally. Which is the most electronegative atom in each of the polar bonds? It's going to be the first one we wrote each time. Of course, it doesn't matter for that one. But the one that was written first is a larger electronegative value. And if you just want to generalize, the further you are on the right-hand side of the periodic table, the more electronegative. The higher, the more electronegative. And that'll be the rule we'll follow for all of them. Okay, end of lecture 2.